Chapter 4 of the ABC of Atoms. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Read by Arden. The ABC of Atoms, by Bertrand Russell. The Hydrogen Spectrum. Chapter 4. The Hydrogen Spectrum. The general lines of atomic structure which have been sketched in previous chapters have resulted largely from the study of radioactivity, together with the theory of X-rays and the facts of chemistry. The general picture of the atom as a solar system of electrons revolving about a nucleus of positive electricity is derived from a mass of evidence, the interpretation of which is largely due to Rutherford. To him also is due a great deal of our knowledge of radioactivity and of the structure of nuclei. But the most surprising and intimate secrets of the atom have been discovered by means of the spectroscope. That is to say, the spectroscope has supplied the experimental facts, but the interpretation of the facts required an extraordinarily brilliant piece of theorizing by a young Dane, Niels Bohr, who, when he first propounded his theory, 1913, was still working under Rutherford. The original theory has since been modified and developed, notably by Sommerfeld, but everything that has been done has been built upon the work of Bohr. This chapter and the next will be concerned with his theory in its original and simplest form. When the light of the sun is made to pass through a prism, it becomes separated by refraction into the different colors of the rainbow. The spectroscope is an instrument for effecting this separation into different colors for sunlight, or for any other light that passes through it. The separated colors are called the spectrum, so that a spectroscope is an instrument for seeing a spectrum. The essential feature of the spectroscope is the prism through which the light passes, which refracts different colors differently, and so makes them separately visible. The rainbow is a natural spectrum, caused by refraction of sunlight in raindrops. When a gas is made to glow, it is found by means of the spectroscope that the light which it emits may be of two sorts. One sort gives a spectrum, which is a continuous band of colors, like a rainbow. The other sort consists of a number of sharp lines of single colors. The first sort, which are called band spectra, are due to molecules. The second sort, called line spectra, are due to atoms. The first sort will not further concern us. It is from line spectra that our knowledge of atomic constitution is obtained. When white light is passed through a gas that is not glowing, and then analyzed by the spectroscope, it is found that there are dark lines, which are to a great extent, though not by any means completely, identical with the bright lines that were emitted by the glowing gas. These dark lines are called the absorption spectrum of the gas, whereas the bright lines are called the emission spectrum. Every element has its characteristic spectrum, by which its presence may be detected. The spectrum, as we shall see, depends in the main upon the electrons in the outer ring. When an atom is positively electrified by being robbed of an electron in the outer ring, its spectrum is changed, and becomes very similar to that of the preceding element in the periodic table. Thus, positively electrified helium has a spectrum closely similar to that of hydrogen, so similar that for a long time it was mistaken for that of hydrogen. The spectra of elements known in the laboratory are found in the sun and the stars, thus enabling us to know a great deal about the chemical constitution of even the most distant fixed stars. This was the first great discovery made by means of the spectroscope. The application of the spectroscope that concerns us is different. We are concerned with the explanation of the lines emitted by different elements. Why does an element have a spectrum consisting of certain sharp lines? What connection is there between the different lines in a single spectrum? Why are the lines sharp instead of being diffuse bands of colors? Until recent years, no answer whatever was known to these questions. Now the answer is known with a considerable approach to completeness. In the two cases of hydrogen and positively electrified helium, the answer is exhaustive. Everything has been explained, down to the tiniest peculiarities. It is quite clear that the same principles that have been successful in those two cases are applicable throughout, and in part the principles have been shown to yield observed results. But the mathematics involved in the case of atoms that have many electrons is too difficult to enable us to deduce their spectra completely from theory, as we can in the simplest cases. In the cases that can be worked out, the calculations are not difficult. Those who are not afraid of a little mathematics can find an outline in Norman Campbell's Series Spectra, Cambridge, 1921, and a fuller account in Sommerfeld's Atomic Structures and Spectral Lines, of which an English translation is published by E.P. Dutton and Company, New York, and Methuen in London. As everyone knows, light consists of waves. Light waves are distinguished from sound waves by being what is called transverse, whereas sound waves are what is called longitudinal. It is easy to explain the difference by an illustration. Suppose a procession marching up Piccadilly. From time to time, the police will make them halt in Piccadilly Circus. Whenever this happens, the people behind will press up until they too have to halt, and a wave of stoppage will travel all down the procession. When the people in front begin to move on, they will thin out, and the process of thinning out will travel down the whole procession, just as the previous process of condensation did. This is what a sound wave is like. It is called a longitudinal wave, because the people move all the time in the same direction in which the wave moves. But now suppose a mounted policeman, whose duty it is to keep half the road clear, rides along the right-hand edge of the procession. As he approaches, the people on the right will move to the left, and this movement to the left will travel along the procession as the policeman rides on. This is a transverse wave, because while the wave travels straight on, the people move from right to left, at right angles to the direction in which the wave is traveling. This is the way a light wave is constructed. The vibration which makes the wave is at right angles to the direction in which the wave is traveling. This is, of course, not the only difference between light waves and sound waves. Sound waves only travel about a mile in 5 seconds, whereas light waves travel about 180,000 miles a second. Sound waves consist of vibrations of the air, or of whatever material medium is transmitting them, and cannot be propagated in a vacuum, whereas light waves require no material medium. People have invented a medium, the ether, for the express purpose of transmitting light waves. But all we really know is that the waves are transmitted. The ether is purely hypothetical, and does not really add anything to our knowledge. We know the mathematical properties of light waves, and the sensations they produce when they reach the human eye, but we do not know what it is that undulates. We only suppose that something must undulate because we find it difficult to imagine waves otherwise. Different colors of the rainbow have different wavelengths, that is to say, different distances between the crest of one wave and the crest of the next. Of the visible colors, red has the greatest wavelength, and violet the smallest. But there are longer and shorter waves, just like those that make light, except that our eyes are not adapted for seeing them. The longest waves of this sort that we know of are those used in wireless telegraphy, which sometimes have a wavelength of several miles. X-rays are rays of the same sort as those that make visible light, but very much shorter. Gamma rays, which occur in radioactivity, are still shorter, and are the shortest we know. Many waves that are too long or too short to be seen can nevertheless be photographed. And speaking of the spectrum of an element, we do not confine ourselves to visible colors, but include all experimentally discoverable waves of the same sort as those that make visible colors. The X-ray spectra, which are in some ways peculiarly instructive, require quite special methods, and are a recent discovery, beginning in 1912. Between the wavelengths of wireless telegraphy and those of visible light, there is a vast gap. The wavelengths of ordinary light, including ultraviolet, are between a 10,000th and about a 100,000th of a centimeter. There is another long gap between visible light and X-rays, which are on the average composed of waves about 10,000 times shorter than those that make visible light. The gap between X-rays and gamma rays is not large. In studying the connection between the different lines in the spectrum of an element, it is convenient to characterize a wave, not by its wavelength, but by its wave number, which means the number of waves in a centimeter. Thus, if the wavelength is 1/10,000th of a centimeter, the wave number is 10,000. If the wavelength is 100,000th of a centimeter, the wave number is 100,000, and so on. The shorter the wavelength, the greater is the wave number. The laws of the spectrum are simpler when they are stated in terms of wave numbers than when they are stated in terms of wavelengths. The wave number is also sometimes called the frequency, but this term is more properly employed to express the number of waves that pass a given place in a second. This is obtained by multiplying the wave number by the number of centimeters that light travels in a second, i.e. 30,000 million. These three terms, wavelength, wave number, and frequency, must be borne in mind in reading spectroscopic work. In stating the laws which determine the spectrum of an element, we shall for the present confine ourselves to hydrogen, because for all other elements, the laws are less simple. For many years no progress was made towards finding any connection between the different lines in the spectrum of hydrogen. It was supposed that there must be one fundamental line, and that the others must be like harmonies in music. The atom was supposed to be in a state of complicated vibration, which sent out light waves, having the same frequencies that it had itself. Along these lines, however, the relations between the different lines remained quite undiscoverable. At last, in 1908, a curious discovery was made by W. Ritz, which he called the principle of combination. He found that all the lines were connected with a certain number of inferred wave numbers, which are called terms, in such a way that every line has a wave number, which is the difference of two terms, and the difference between any two terms, apart from certain easily explicable exceptions, gives a line. The point of this law will become clearer by the help of an imaginary analogy. Suppose a shop belonging to an eccentric shopkeeper had gone bankrupt, and it was your business to look through the accounts. Suppose you found that the only sums ever spent by customers in the shop were the following: 19 shillings, 11 pence, 19 shillings, 15 shillings, 10 shillings, 9 shillings, 11 pence, 9 shillings, 5 shillings, 4 shillings, 11 pence, 4 shillings, 11 pence. At first these sums might seem to have no connection with each other, but if it were worth your while you might presently notice that they were the sums that would be spent by customers who gave 20 shillings, 10 shillings, 5 shillings, or 1 shilling, and got 10 shillings, 5 shillings, 1 shilling, or 1 pence in change. You would certainly think this very odd, but the oddity would be explained if you found that the shopkeeper's eccentricity took the form of insisting upon giving 1 coin or note in change, no more and no less. The sums spent in the shop correspond to the lines in the spectrum, while the sums of 20 shillings, 10 shillings, 5 shillings, 1 shilling, and 1 pence correspond to the terms. You will observe that there are more lines than terms, 10 lines and 5 terms, in our illustration. As the number of both increases, the disproportion grows greater. 6 terms would give 15 lines, 7 terms would give 21, 8 would give 28, 100 would give 4,950. This shows that the more lines and terms there are, the more surprising it becomes that the principle of combination should be true, and the less possible it becomes to attribute its truth to chance. The number of lines in the spectrum of hydrogen is very large. The terms of the hydrogen spectrum can all be expressed very simply. There is a certain fundamental wave number, called Rydberg's constant, after its discoverer. Rydberg discovered that this constant was always occurring in formulae for series of spectral lines, and it has been found that it is very nearly the same for all elements. Its value is about 109,700 waves per centimeter. This may be taken as the fundamental term in the hydrogen spectrum. The others are obtained from it by dividing it by 4, twice 2, 9, 3 times 3, 16, 4 times 4, and so on. This gives all the terms. The lines are obtained by subtracting one term from another. Theoretically, this rule gives an infinite number of terms, and therefore of lines. But in practice, the lines grow fainter as higher terms are involved, and also so close together that they can no longer be distinguished. For this reason, it is not necessary, in practice, to take account of more than about 30 terms, and even this number is only necessary in the case of certain nebulae. It will be seen that, by our rule, we obtain various series of terms. The first series is obtained by subtracting from Rydberg's constant successively a quarter, a ninth, a 16th of itself, so that the wave numbers of its lines are respectively 3/4, 8/9, 15/16 of Rydberg's constant. These wave numbers correspond to lines in the ultraviolet, which can be photographed but not seen. This series of lines is called, after its discoverer, the Lyman series. Then there is a series of lines obtained by subtracting from a quarter of Rydberg's constant successively a 9th, a 16th, a 25th of Rydberg's constant, so that the wave numbers of this series are 5/36, 3/16, 21/100 of Rydberg's constant. This series of lines is in the visible part of the spectrum. The formula for this series was discovered as long ago as 1885 by Balmer. Then there is a series obtained by taking a 9th of Rydberg's constant and subtracting successively a 16th, 25th, etc. of Rydberg's constant. This series is not visible, because its wave numbers are so small that it is in the infrared, but it was discovered by Paschen, after whom it is called. Thus, so far as the conditions of observation admit, we may lay down this simple rule. The lines of the hydrogen spectrum are obtained from Rydberg's constant, by dividing it by any two square numbers, and subtracting the smaller resulting number from the larger. This gives the wave number of some line in the hydrogen spectrum, if observation of a line with that wave number is possible, and if there are not too many other lines in the immediate neighborhood. A square number is a number multiplied by itself. 1 times 1, twice 2, 3 times 3, and so on. That is to say, the square numbers are 1, 4, 9, 16, 25, 36, etc. All this, so far, is purely empirical. Rydberg's constant, and the formulae for the lines of the hydrogen spectrum, were discovered merely by observation, and by hunting for some arithmetical formula which would make it possible to collect the different lines under some rule. For a long time the search failed, because people employed wavelengths instead of wave numbers. The formulae are more complicated in wavelengths, and therefore more difficult to discover empirically. Balmer, who discovered the formula for the visible lines in the hydrogen spectrum, expressed it in wavelengths, but when expressed in this form, it did not suggest Ritz's principle of combination, which led to the complete rule. Even after the rule was discovered, no one knew why there was such a rule, or what was the reason for the appearance of Rydberg's constant. The explanation of the rule, and the connection of Rydberg's constant with other known physical constants, was effected by Niels Bohr, whose theory will be explained in the next chapter. End of chapter 4.